Welcome back, everybody. In this lecture, we are going to discuss polynomial factoring. So we want to factor polynomial functions. The question says fully factor this quartic polynomial. And in order to do this, we are going to use the factor theorem. We're going to say we need to find a value of a, some number a, such that f at a is equal to 0. The only possible value of a are divisors of the constant term in f of x. So I wish we knew if this polynomial is divisible by x minus 1 or x minus 6 or something, because then we could divide this by that factor and then reduce the degree of the dividend, which is 4, into 3. And if you could do this another time, like second time in a row, then we could reach a quadratic factor and simply factor it using known methods. So we look at the constant term here, 12, and we list all the divisors of the 12. Plus minus 1, plus minus 2, plus minus 3, 4, 6, 12, but not 7, not any other number. So these are the factors, or not factors, divisors of 12. So these are good candidates for the so-called a value. So what we're going to do, we're going to try to find f at these numbers, and we cross our fingers, maybe we can reach a 0 and apply the factor theorem. So f at 6, we're going to plug in. So I'm going to say 6 to the power of 4 minus 3 times 6 cubed minus 13, 6 squared, and we can use a calculator. And when you do the math using the calculator, unfortunately, you end up with 210. So 210 is not equal to 0. That means that you cannot say x minus 6 is a factor of f of x, or you cannot say f of x is divisible by x minus 6, because f at 6 simply was not equal to 0. We were hoping that it would, but it did not. We tried picking another candidate. We have 2, 4, 6, 8, 10, 12. We have 12 candidates there to select. I selected 6 first. Now I'm selecting 2. What is f at 2? So when you do the f at 2, you get 16 minus 24 minus 52 and plus 6 plus 12, which again, we don't care we don't care about the number. As long as it's not 0, that's all what we want to know. So this sum is not equal to 0. We are interested in 0. But if it's not 0, then we don't care what number it could be. But it's not 0. Clearly, when you add them up, you don't get 0. So we see that f at 2 is not 0 either, which means that x minus 2 is not a factor of this polynomial. So we're going to try picking something else. I picked 6, I picked 2, and it was unsuccessful. This time I picked negative 1. Or actually, I picked positive 1. So when you plug in 1, for x, we get 1 minus 3 minus 13. And sure enough, this time we have 15 and negative 15. That is actually a 0. So the moment you get the 0, you can use the factor theorem. You can say, therefore, x minus 1 is a factor of f of x, or f of x is divisible by x minus 1. So we found one of the factors of this quartic polynomial. To find another factor, so we're going to try another number. So we used divisor of 6 and 2. We were unsuccessful. We used a divisor of 1. We were successful. F at 1 actually was 0. And now we try f at negative 1, another divisor. And this one becomes 1 plus 3. And sure enough, it is again equal to 0, luckily. So we may say that x plus 1 is a factor of f of x. Okay, so we found two factors, x minus 1 and x plus 1. So now we know that this polynomial, quartic polynomial, is not only divisible by x minus 1, but also it's divisible by x plus 1. So now that we know this, we're going to say, therefore, x minus 1 and x plus 1 are factors of f of x. So now we can start dividing, actually, expecting to get a remainder of 0. But you know that long division is very long. We don't want to do a procedure that is time consuming. We want to quickly find the answer, okay? So that's why we are using synthetic division, which is a very fast method. So I wrote the coefficients, and now I'm going to perform this very quickly. The root of the divisor is 1. So we bring 1 down, 1 times 1, 1, add them up, -2, times that -2, add them up, -15, times that 15, add them up, 18, times 1 is 18, and add them up. So something somewhere is wrong. We might have made a mistake because, yes, my mistake is -15 times 1 is -15. I wrote +15, so that's why I knew that there must be something somewhere wrong. So now when you add them up, 3 and -15, it gives you -12 times 1, -12, and we are getting a remainder of 0 as it was expected. Okay, so the quotient here, I can call this like quotient number 1. This would be x cubed minus 2x squared minus 15x minus 12. Okay, so this expression, this cubic expression times x minus 1 is equal to the original quartic polynomial. But now we know that x plus 1 is another factor of the original polynomial. So that x plus 1 must be a factor of this cubic polynomial as well, because it is factor of the original one. So again, we're going to perform another synthetic division instead of using long division, which is time consuming, and dividing this cubic polynomial by x plus 1 this time. So the root of the divisor is -1. We write the coefficients and quickly perform the synthetic division. So 1 times -1, add them up, -3, times that 3, add them up, -12, times that +12, add them up, 0, and this is what we were expecting to end up with a remainder of 0. So now we have another quotient here. I call this q sub 2 of x. It's x squared minus 3x minus 12. Okay, so to summarize, we had one factor of x minus 1 and then x plus 1, and now we have this quotient of x squared minus 3x minus 12. So if you want to factor this trinomial, you're going to see that it's impossible to factor it because it's not factorable simply. Two numbers add up to -3, the product of -12. We cannot find such two numbers, therefore this quadratic trinomial is not factorable. So if it's not factorable, you don't factor it, you leave it as it is. So f of x, the quartic polynomial, is factored in this form. It's equal to x minus 1 times x plus 1 times this quadratic expression. Sometimes even this one is factorable, then you can factor it using the grade 10 methods you have learned in the past. Using the known methods, you can factor it. Sum and product method, decomposition method, trial and error method, all sorts of methods are out there. But if it's not factorable, like in this case, you're going to leave it as it is. I just want to add one more thing here, that these kind of questions are related to polynomials where the coefficient of x to the 4 or the leading coefficient is 1. Okay, if the leading coefficient is not 1, then we still can use factor theorem, but we use factor theorem extended, we call it. So in the next lecture, I'm going to talk about that. But for now, if the coefficient of x to the 4 or x to the 5 or x cubed, whatever it is 1, then that's how you do it. Very straightforward. If it's not equal to 1, if it's like 2 or 3 or something else, we just have to do a little bit of fine-tuning at the very beginning, and then the rest of the procedure is the same. But I'm going to give you examples for sure. If you want to do some practice questions, there's a cubic polynomial for you to factor, x cubed minus 5x squared minus 2x plus 24, and the answer is going to be x plus 2 times x minus 4 times x minus 3. So look at the constant term, which is 24. In my case, it was 12, and list all the divisors of 24, okay? And then pick and choose and see f at which one of those divisors would be 0. Luckily, you can get, one or two zeros. In this case, you get one that's enough because it's cubic, but in my case, it was quartic. I had to find two factors. So try different f values at different divisors. See which one is 0. The moment that you got the 0, you should get happy and you should use the factor theorem. Okay, so the final answer to this question is this. The question says fully factored, and we did actually fully factor. Thank you for your attention, and we will meet again at the next lecture.